Today we're going to talk about structural isomers. Structural isomers are different arrangements of the same atoms with different properties. So you're not changing the number of atoms, you're just changing where those atoms are located. If you're given the molecular formula and not sure of the Today we're going to talk about structural isomers. These are arrangements of the same atoms with different properties. The number of isomers increases as the size of the molecule increases. So, for example, if you're just given C6H14, you could draw that in different ways. The most common way of doing it would be to draw the straight chain of 6 carbons. Now, if you notice, this is N, and then this would be 2N plus 2, so we know that these are all single bonds. So we could draw carbon, and then put in our hydrogens, and so we would have hexane. However, we could rearrange this by removing one of the carbons and putting it as a side group. You would have a 5-carbon chain and then a side group. So this would be 2-methyl pentane. Now that side chain wouldn't have to be on the second carbon, it could be on the third carbon. So we could draw another structure where the side chain is coming off of the third carbon. So this would be 3-methyl pentane. So these are 3 isomers of C6H14. Now we can keep going and take another carbon off of the main chain and create a side group with it. So if we just had a chain of 4 carbons, we could put a methyl group, 1 methyl group on each of those, and so we would have 2,3-dimethyl, and then 4 carbons would be butane. Or we could take those 2 and we could put them on the same carbon. And so we would have 2,2-dimethyl butane. Now, if you draw that same one but decide to put it on this carbon, notice that that's the same exact molecule, so that is not a different isomer. And so C6H14 has 5 isomers. If you had a double bond, you can create an isomer just based on the location of that double bond. So here the double bond is on the first carbon, we move it to the second carbon. Now we can't move it to the third carbon because then that would be the same thing as 1-butene. So if you have a double bond, you simply just move the double bond through the chain until you start repeating it. Here we have a triple bond, and you can see we're moving that triple bond through the chain. You could also have a side group with that triple bond moving through the chain. So you take your chain, move your double or triple bonds if they're there, and then start removing 1 carbon and turning it into a side group instead of being on the main chain. That's the most common way of forming the isomers. You can also have isomers with functional groups. So a lot of our functional groups contain oxygen, and so we could create the C2H6O has the same formula. This is a hydroxyl group, so this is an alcohol, where we could put the the oxygen in the middle and make it an ether. So you can also take your structures and move the oxygen so that you get different functional groups. So if we take an example, C4H10O, and we can draw the different functional groups. So the first thing I would do is chain my 4 carbons. If I add in hydrogens, I notice that I would have to have an alcohol. I can't double bond that oxygen because I have a hydrogen that would have to be put on there. So this would be bute and 1-ol. Now some of you notice that the hydroxyl suffix is ANOL. Typically you put the number in between the AN and the OL, so it's buten 1-ol. It just sounds better that way. Now we could have that alcohol group, instead of being on the first carbon, on the second carbon. So we draw our chain, and then we can move that hydroxyl group, and this would be buten 2-ol. Alright, so then once you've moved, we can't move it again because we'd get the same molecule. So then we're going to remove a carbon from the longest chain and make that a side group. So now our longest chain is 3 carbons. We have our alcohol or our hydroxyl, and then we have a side group. So this would be 2-methyl, and it's on the second carbon because the first carbon has to have that functional group on it. Prop, 3 carbons, and 1-ol. So that alcohol is on that first carbon. We could move that alcohol back to the second carbon, and so we could have it look like this, where our side group and the functional group are coming off of the same carbon, and we would have 2-methyl prop and 2-ol. Those are all the different types of hydroxyl groups that we can have. So then we have to think, is there another place we could put that oxygen? So we could put the oxygen within the chain. So you have your 4 carbons chained together, and an oxygen is splitting them. So this, remember, has that special naming where you want to name the smallest chain and then put oxy and then the bigger chain. So this would be meth, oxy, propane. So meth for the one-sided carbon, and then you have the 3 carbons on this side. We could move the oxygen to be directly in between. And so we would have oxyethane, where we have 2 carbons on one side, 2 carbons on the other side. We could also take those and make a side group for one of the carbons. So you could draw this as well, and so the name would be 2-methoxypropane. The 2 is saying what carbon the methyl side group is on, and then because it says oxy, we know there has to be a side group continuing after, or a carbon continuing after the oxygen, so that naming is a little different than what we're used to. When we talk about where the alcohol group is located, we can also refer to them as being primary, secondary, or tertiary. So tertiary refers to like tri or 3, not 4, but 3. So primary, secondary, tertiary. And it depends on how many things the carbon atom is attached to. So if the carbon that has the alcohol on it has 2 other hydrogen atoms, it's primary. If there's only 1 other hydrogen, then it's secondary, and if it has no other hydrogens, then it's tertiary. So for example, with the alcohol here, you have the primary because the carbon has 3 hydrogens, secondary because there's only 1 hydrogen, and then tertiary because there's no other hydrogens. You could have primary, secondary, or tertiary halogens as well, and that's what's shown up here. And then our amines can do the same thing. although the definition of primary, secondary, tertiary is a little bit different there. Instead of counting how many hydrogens are on the carbon, we're counting how many carbons are attached to the nitrogen.